Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. Today's topic, we will see the physical significance of conservative and non-conservative forms of equations in CFD. So, we'll basically see what is conservative form and what is non-conservative form, and we will also see their equations and whether these two equations have any significance in computational fluid dynamics in determining the fluid flow problem. We will see it. So here, as we discussed, there are four types. So of defining the fluid flow. So one is called CV, which is control volume approach. Control volume. So other one is fluid element. Okay. So here basically control volume can be stationary or it can be movable. Fluid element can be stationary or movable. So let us take this as a control volume CV. Okay. So this is stationary in the sense the velocity. So the velocity of CV is equal to 0. So this is one approach. So you take another control volume CV. So this is CV1. Let's say this is CV2. So velocity of CV is not equal to 0. So this is condition 1 and this is condition 2. So here there are in thermodynamic entities, look, we have seen basic things. So the outer part, which we call it as boundary. Okay. So this one is called surroundings. Okay. And this one is called system. Okay. Or let's say environment. Fine. So external environment, we can say. The boundary is the phase which is actually differentiating the environment with the system. System is nothing but the entity where there is change in fluid flow properties. So actually let us take environment. So this point we can take environment. So whether this one we can take environment, whether this point. So point P1, P2, P3 is available. So let's say as we going far from the system entity, so which one has to be considered as the environment variable. So whether P1 can be considered or whether P2 can be considered, whether P3 can be considered. So which one has to be considered, that is very, very important. So when, like, if we consider P1, P2, P3, so if the presence of system is making any changes near P1, then you can consider P1 as your environment variable. So even if it is affecting P2, so even you can take this as the affecting variable. So P3 is nothing but 0.3. So P3 is nothing but 0.3, where if the influence of system on this point is 0. So let's say you have a hot fluid, or let's say hot element which is 300 degrees Celsius. So because of this hot element, so if you have any change that happens near P1, P2, then you can consider these P1, P2 as your surrounding variables. When you take this as P3, so let's say this is P3. So P3 is nothing but the entity where, so the effect of this system here, it is 0. There is nothing effect here. Fine. Now, so boundary is the entity where it is dividing the system with the surrounding. Fine. And if the velocity of control volume is 0, so what is the meaning actually? So the entity is not at all moving, first of all. Fine. So the entity is not at all moving, and here the fluid which is entering it will leave with certain velocity. Okay, V in and V out actually. So here when the fluid is entering to the control volume, so it will undergo some changes or effects because of the system properties, and that changes, whatever it is happening, will be studied and then it is left out actually. So this is what happens. Fine. So when this fluid is entering, so we have to see what are the properties that is affecting the control volume and how the fluid is affected. Fine. So let us take an example of a person going on bike, or let's say you take airplane. So when airplane is stationary, there is no movement of like let's say body relative to the air. So therefore the flow can adjust over the aircraft and move smoothly. When aircraft has certain velocity, let's say equal to speed of sound or greater than speed of sound, so the air which is striking the aircraft is getting affected actually, and that effect will be studied in the CFD. And then whatever the changes that is happening for the aircraft, let's say you have the deformation of the wing, or the deformation because of the wing load, or any other entity, so this can be in detail studied over the wing actually, or let's say any body. So this is what we do. So when we see the control volume approach, so we will integrate over the volume. So we will see the volume integral. So every time we will see the volume integral, and when this control volume is stationary, so the whatever velocity we have, it is corresponding to the fluid or the air velocity. So there is nothing like relative velocity. Fine. So for example, let us write down the momentum equation. So sorry, continuity equation, where the rate of decrease of mass inside the control volume. So decrease is nothing but negative. So the rate is nothing but dou by dou t. And when you do the volume integral, so the meaning is whatever the change that is happening inside the volume, so into rho dv. So the rate of change or rate of decrease of mass inside the control volume is equal to the flow or the flux which is leaving outside the volume. So you can see this is the surface integral. So rho v dot ds. So this is what we have. Fine. So here you can see clearly dou by dou t. So volume integral rho dv, which is equal to the surface integral rho v dot ds. So here you can see that the negative symbol is showing the decrement inside the control volume, and dou by dou t is the change that is happening inside, and rho dv is nothing but the mass, so which is changing inside the volume. And here you can see rho v dot ds. Rho v dot is nothing but the flux which is leaving the surface. Okay, so that is what we have. Here the velocity, here you can see that velocity is absolutely the flow velocity. In the second approach, what happens actually, so it will move along with the fluid, or let's say it may have certain velocity. Example, we can say like since aircraft is moving with certain velocity, aircraft engine will have some intake of air. So when the air intake is happening, what happens actually, so the fluid will enter with certain velocity, the engine also moving with certain velocity, the relative velocity has to be calculated. Fine. So here the modified form, so what happened actually, minus dou by dou t, you can see the integral rho dv, which is equal to, so the surface integral rho, actually here v minus vc, the relative velocity dot ds. So you can see in this way. Fine. So this is what happens for a change of control volume which is moving with the fluid. This is for the second entity. So this is for the first entity and this is for the second entity. Fine. So this is what we have. Next, so we have one more approach called the fluid element approach. So here you can take this as fluid. Fine. So here same, here the velocity of the fluid is like fluid particle. Here let us take this is 0, and the other one you can take this as, so Vf is not equal to 0. Fine. So here what happens actually in the first setup, so since the velocity of the fluid particle is 0, so whatever the flow that is entering and crossing, so there will be a change of number of molecules, the entity that happens. Here for the second one, so since it is going with the flow, so same number of fluid particles will be present inside the element every time.
పవర్ వద్దంట జనరేటర్ ట్రాన్స్ఫార్మర్ మార్చుతారంట అని చెప్తావా మరి అట్లా 5 minutes అయిపోతుందా నీ ఇష్టం అది 5 minutes క్లోజ్ చేసి చెప్పు
5 minutes close. Okay, so Vf is equal to 0. Fine. So next the element whatever we have, Vf is equal to 0, Vf not equal to 0. So here we get the equation in the form of differential form, so which is d by dt minus d by dt of rho dv, which is equal to, so d by, or let's say you can say gradient of this del dot rho v. Okay, so here this is surface integral actually ds. Fine. So here the difference between these two, what happens, so here the velocity of the fluid, here you can see it is 0, here it is non-zero, then here the relative Vf minus V minus Vf. This is what happens. So when we compare whether you take the fluid element approach or whether you take the control volume approach, so when the fluid element is moving with the space, they are called non-conservative form, or when the control volume is moving with the space, that is called non-conservative form. And when the control volume is stationary or the fluid element is stationary, then they are called conservative form. Fine. So this conservative form and non-conservative form of equations, whether you take conservative form or whether you take non-conservative form, the physics of the flow will not change, but the relative velocity so will be taken into account. So that is the difference of what we will observe. Okay, so with this we have seen the physical significance of the conservative and non-conservative form of equations for the CFD in the fluid flow phenomena. In the next lecture we will see some other aspects such as substantial derivative and how the fluid particle changes with respect to time and space, what is local acceleration, convective acceleration. Already we have seen, we'll just see in detail in the mathematical form. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.